So this section of the unit deals with percent composition, and I thought maybe it would help to start with a simple analogy. Consider a cheeseburger. So if we have one cheeseburger, let's just say for simplicity that the cheeseburger consists of, a hamburger bun, uh, the um, the hamburger, and cheese. Okay, so let's say we send our cheeseburger out for mass analysis. We send it to our top scientists, and we determine that in terms of mass, the bun turns out to be, let's say, 5 grams, and the hamburger turns out to be, 25 grams, and the cheese adds 5 grams. Okay, and we could very well ask the question, well, in terms of percent mass, what percent of the total mass of our cheeseburger is coming from the bun, and what percent of the mass is coming from the hamburger, and so on. And if we were to do that, it'd be pretty straightforward, right? Because intuitively, you know that if you're going to try to figure out what each of the three components is in terms of percent mass, we're going to have to add the total mass contributions from each of the three components. And so this would give us a total of 35 grams. That's our total. Okay, so then if we want the percent coming from the bun, that would be 5 grams, which is the bun, divided by 35 grams, which is the total. And then if we want that in terms of a percentage, then you've got to multiply that by 100. And let's see, let's do that. 5 divided by 35 times 100 would be 14.3%. Okay. Likewise, the percent of the hamburger, I'll just abbreviate H for hamburger, then that would be 25 grams divided by 35 grams times 100. And let's see, that would be 25 divided by 35, 71.4%. And we know that since the cheese has the same mass as the bun, the percentage would be the same, 14.3%. Okay, so that's percentage from the cheese. And when you add all that up, it's going to come out to be 100%, which, it has to. So in sort of in a simplistic example, this is exactly the same procedure that we're going to use for calculating the percent composition of a compound as contributed from each of its constituent elements. So that's what problem number 1 consists of in your homework. So why don't we do that together? Let me see if I can clear the area here. Okay, great. Make it a little bit bigger. Okay, hopefully you can see that there at home. Let me get my pen back. So here we have an example where we have a compound. It's been analyzed, and they have determined that 5.34 grams is coming from carbon, 0.42 grams from hydrogen, 47.08 grams from chlorine. So this is a 3-element compound. And so the first thing we have to do to get the percent composition coming from each of the 3 elements is we got to add all the masses together. All right, so we know we got to do that. And when you do that, you should come up with a total mass of 52.84 grams. All right, so then if you want the percent composition from, say, carbon, then we take the 5.34 grams that's being contributed to total mass from carbon, and you divide that by 52.84 grams, multiply by 100, and you'll get 10.1%. 10.1%. Likewise for hydrogen. Now I won't do everything out here, but when you take 0.42 and divide by 52.84, multiply by 100, you'll get 0.79%. And percent chlorine, you'll take the 47.08, divide that by 52.84, multiply by 100, and you should get 89.1%. Okay? And then if you add up these, this should come out to be right around 100%. Sometimes you'll, because of small rounding errors, your total percentages might come out to be, 100.1 or 99.9, but those are, rounding errors. As long as you can get it in this ballpark, you're doing fine. Okay, so that is an example of how you'd work number one. Let's try a little different type of problem. Number 4 represents a little different variation. Let's read the problem here. From the formula for calcium acetate, and there's the formula, calculate the mass of the carbon that could be obtained from this compound if you had 65.3 grams of it. Okay, so if you had 65.3 grams of this stuff, some percentage of that total mass is going to be attributable to the carbon in the compound, and then some of it's going to be coming from calcium, some from hydrogen, some from oxygen. So our first, before you can determine exactly how many grams of this compound is due to carbon, we need to determine the percentage of the mass that's coming from carbon. Okay, so calculating percent mass is an easier job than getting the the mass of the carbon right off the bat. All right, and here's how we do that. You can assume that you have 1 mole of the stuff. Okay, so assume 1 mole. And so if you had 1 mole of this stuff, you'd go over here and you'd calculate the molar mass. So calcium 40.1. Let me adjust the thickness here. I feel like my writing is sloppy. Carbon, you have 4 carbon atoms, so that's 48.0. You have 6 hydrogens, so that's 6.0. And you have 4 oxygens, and so the total there is 64.0. And when you add everything up, the molar mass is 158.1 grams. Okay, so if you had 1 mole of this stuff, then you could easily calculate the percentage of the mass that's coming from the carbon, right? Because you know the atomic mass of carbon, and you know how many of them you have. So you just take the total atomic mass coming from carbon, divide that by the total molar mass, and lo and behold, you'll have the percentage of the mass coming from carbon. Okay, gram times 100. And when you do the calculation, you should get 30.4%. Okay, so then what you do is now you know the percentage of the mass of this compound that's coming from carbon. And so you take 30.4%, and when you apply that to the total mass of the actual compound that you've got, that turns out to be 19.8 grams. Okay, so another way to say this is 19.8 grams of this 65.3 gram sample is carbon, and you have to go through the molar mass in order to solve that. Okay, let's just checking my time. All right, we're doing good. Okay, now let's go to number 7. Let's try number 7. So numbers 5 and 6 are pretty similar to number 4. Okay, use the same strategy. All right, let's try number 7. So this is yet a third variation on calculating percent composition. It says determine the empirical formula of each of the following compounds from the percent composition. And the first one we have, compound A, we pretend that they've taken this compound to the lab, they did elemental analysis and determined that 7.8% of the compound is carbon, and the balance, 92.2% of that compound, is chlorine. Now, to solve this kind of a problem, well, let me back up. They're asking you for the empirical formula. So you've got to know what an empirical formula is, and from your book, it says on page 309 toward the bottom that the empirical formula of a compound shows the smallest whole number ratio of the atoms in the compound. Okay, so at the end of the problem, we're going to have a formula where we're trying to determine the smallest whole number ratio of the atoms in the compound. So it could be, for example, could be CCl3, CCl2. We're not sure. I think you probably have a hunch of what it's going to be, but let's try to do this step by step. Okay, so here is the little trick that you can do. It's very straightforward, very clever. These are percentages. So what we can do is let's pretend that we have 100 grams, exactly 100 grams of the compound. And if we had 100 grams of this compound, then we would have 7.8 grams of carbon, and we would have 92.2 grams of chlorine. So that's perfectly all right to assume this. This would give us 7.8% and 92.2% chlorine, right? Okay, now take both of these and convert those masses to moles. And once we get those two masses to moles, then we can compare the ratio of the two moles, and that will then lead us to the the X and the Y, the subscripts. All right, so let's do this. So let's convert 7.8 grams of carbon to moles, and I think you got to divide that by the molar mass, or the atomic mass of carbon, which is 12.0 for our purposes. And when you do that, you find that the number of moles of carbon is 0.65 moles. And when you do the same thing for chlorine, what you find is that you have 2.60 moles of chlorine. All right, so that's what you get when you divide 92.2 by 35.5. Now, clearly you have more moles of chlorine than you have of carbon, and so then the mole ratio of chlorine over carbon is 2.60 divided by 0.65, and when I did this on my calculator, I got something like 3.9956 blah blah blah, which is about as close to 4 as you can get. And so what that implies is that the ratio is 1 to 4. That is 1 carbon for every 4 chlorines, and that is the empirical formula. Okay, thanks. We'll see you tomorrow.